Well, here we are again. So to begin with, are there any questions? So everybody's up to date, okay? All right, so what I want to do is I want to finish up, I hope, today, the theory so that we can get that out of the way and start looking at these models in more, from a more practical point of view. So what we were talking about is the birth and death process. And we saw that if you make certain assumptions called the birth and death postulates, then you can derive certain equations which can allow you to calculate these probabilities, which we're going to use to describe the performance of these queuing systems. But we still have to make the connection between the queuing systems and the postulates for the birth and death process. Now, we saw that we're 90% of the way there, because we saw that if we have a Poisson process that generates the births or the arrivals, then that satisfies one of the postulates for the birth and death process. And if we have exponential service times, then for the deaths, that satisfies another of the postulates for the birth and death process. But we have to put the two of the things together and be a little bit more general. So I want to show that if I have this process, or if I have this queuing system in which I have arrivals that are generated somehow by exponential variables, and I have service requirements that are generated by exponential variables, then putting all that together, that's going to lead to satisfying the postulates for the birth and death process. So from that point on, then we can take over the results, namely the formulas we have, or the rate up equals rate down argument to derive the probabilities for any particular case. So let me remind you what the postulates are for the birth and death process. So in the birth and death process, we have a population, and the population size grows or shrinks by one unit at a time. And so we can look at it like this. Here are what can happen. I could start out in state J, and the state corresponds to the number of customers present, or the population size. And I'm in state J for a while. I can't see this because of the reflection, so I don't know whether it's dark or not. Okay. All right, well, we're in state J, and we stay in there a while, and then there's an arrival, and we jump to state J plus 1. So that's one possibility in an interval of length h. So we're going to imagine that this length of time that I have right here is an interval of length h, and this will correspond to having a single arrival or a single jump up in the interval of length h. Now, I could also, starting from state J at the beginning of the interval, I could have a jump down. So I would jump down. This would be state J plus 1, and this would be state J minus 1. Or I could do neither. That is, I could start in state J and end in state J. Or I could do other stuff, which concerns jumping to taking multiple steps. So I'll just do something like that. Okay, now, the birth and death postulates say that the probability that this is what actually occurs is given by lambda sub j h plus little o of h. And the probability that this occurs is given by mu sub j h plus little o of h. Okay? In these expressions, the lambdas and the mu's, these correspond to what are called the birth or death coefficients, and we allow them to depend on the population size at the beginning of the interval, and we say that the probability that we're going to have, for example, this diagram occur, this birth, is proportional to the length of the interval. The proportionality constant is lambda sub j, and then there's this little error term. And the error term has the property that if I divide this by h and let h go to 0, then the ratio goes to 0. And similarly for this statement. And then the other one corresponds to neither of those. So that probability is 1 minus lambda sub j plus mu sub j h plus little o of h. And this guy here has probability little o of h. So these are assumptions, and I want to show that if I have births generated by an exponential process or exponential processes and death generated by exponential processes, then the probabilities that are produced by those assumptions are exactly what's stated here. And that means that we satisfy the criteria, the conditions for the birth and death process, so then we could take over that machinery. So I'm going to do it by simply looking at one of these. I'll look at this one, and if I can derive this value, assuming that I have exponential random variables driving these births and deaths, if I can do this one, then the others are the same kind of reasoning. Okay, so here's the argument. First of all, let's look at this in a little bit more detail here. So here is time 0. And I'm going to be in state J at time 0. So there's going to be a length of time that's going to elapse. I want to calculate now the probability that what actually happens is this piece right here. So there's going to be a length of time that's going to elapse, and then in this example what happens is a birth occurs. So what that means is that there's a bunch of processes racing against each other. So there's some parameter here which I'm going to call lambda sub j, which corresponds to the sum of the arrival rates of all of the birth processes. For example, I could say that I have a bunch of sources, let's say, and each source has an exponentially distributed length of time until that source is going to make a request for service. And so the time until the next request for service is the minimum of those. And if each of those is exponential and they're independent of each other, then as we know, the time to the minimum is also exponential, and its rate is the sum of the rates. So the requirement here then is that if I combine whatever it is, whatever the exponential processes are that are producing the arrivals, that the sum of their rates is what I'll call lambda sub j. In other words, I'll allow that to depend on the state of the system. Okay, so we have lambda sub j is the parameter that corresponds to the exponential time until the first arrival occurs, the next arrival, the minimum of all arrival processes that may be contributing to this particular system. Now, similarly, there's a death process. So at the beginning of the interval, maybe I have, let's say, I might have j customers in service. And the length of time, and I'm going to assume that their service requirements are exponentially distributed, which means that the time until the next death or the next service requirement ends, that time would be the minimum of those exponentials, so therefore its parameter would also be exponential. So I'm going to call that mu sub j. I think the problem here is not the marker but the board. Let me try another one. Okay, so this corresponds to the parameters that describe the exponential distributions that generate the births, and this corresponds to the parameters that generate the exponential distributions that generate the deaths. And the time until the next transition is going to be the minimum of the time until the next birth or the next death. And so if this corresponds is a parameter of an exponential, and this is a parameter of an exponential, then the minimum is also exponential, and its parameter is the sum of those two parameters. So let me call that sum alpha sub j. So alpha sub j now is the length of time until the shortest of all of the competing processes that are going to produce births and deaths occur. And my assumption is that all of those processes are exponentially distributed, although they could have different parameters. But ultimately, I'm allowing those parameters to depend on the population size at the beginning of the interval but not the time. Okay, so this corresponds then to the parameter for the exponential distribution, that is the time from 0 until the next event, be that a birth or a death. Now, in this particular case, we're going to calculate the probability that we have a step up that looks like this, which means that we now have a new parameter here, because once this step occurs, now we're at a higher level, and we don't know what happened except that a birth has occurred, but all the exponential distributions that were in process before, they continue where they left off by the Markov property. So I'm going to call the new parameter alpha sub j plus 1. And then there's the end of the interval, h. So I want to calculate the probability now that this diagram occurs, and this diagram reflects the fact that in the interval between 0 and h, I have exactly one birth in the aggregate. That is, I step up by size 1. So now I'm going to write an integral that represents this probability and show that when I get done and evaluate that integral, it's going to give me as its answer exactly that. So this is obtained by saying, well, I have birth processes and death processes. That is, I have inter-arrival times and I have service times, which are assumed to be exponentially distributed and are racing against each other. And since they're racing against each other, that means that a transition occurs when the race ends. That is, the shortest one occurs. And if the shortest one is an arrival, then I jump up. And if the shortest one is a departure, then I jump down. And it must happen only once, because that's the assumption, is that in the interval of length h, we can have at most one jump up, one jump down, or no jump. Okay, so what's this probability? So first of all, let me calculate the probability that this jump right there occurs at time u. So here's 0, here's h, and here is some time u in between. The u and the h look too much alike here. Okay, what's this probability? Well, this interval is exponentially distributed with parameter alpha. So its density function would be alpha sub j e to the minus alpha sub j u, and then I multiply that by du. So this now represents the probability that the first jump occurs between u and u plus du. That is, the first jump, either a birth or a death. Okay, now I want this to be a jump up, so I want to multiply this by the conditional probability that given that the first jump occurs at u, that it's a jump up. Well, we know that if we have a race among exponentials and the two runners in the race, one has parameter lambda and the other has parameter mu, the probability that the one with parameter lambda wins the race is the ratio of lambda over lambda plus mu. Or in other words, it's lambda j over alpha j. And an important point here is that we proved in class that if we have a race among exponentially distributed runners, that the length of the race and the identity of the winner of the race are independent. So that's used right here, because what I'm saying, first of all, is I know how long the race lasted, it's u. And then second of all, I'm saying regardless of who won that race, regardless of how long it lasted, the probability that it was won by the arrivals as opposed to the departures would therefore be lambda j over alpha j. Okay, so we use that theorem. Now what must happen is, and then in the remaining interval between u and h, nothing must happen. So in other words, this exponentially distributed variable, whose parameter is alpha sub j plus 1, must not terminate. So what's the probability of that? Well, it would be, let's get rid of this little o of h here. It would be e to the minus alpha sub j plus 1. That's the parameter for that exponential. And the length of the time here is h minus u. H minus u. And that has to be integrated as u runs between 0 and h. Okay, so all the stuff that we've done before is now included in here. That's why we did it. Okay, so the argument goes, first of all, we want to have the race between arrivals and departures end at time u. What's the probability of that? It's the density function of the length of the race times du. That gets me an event occurring here. Then I want that event to be an arrival because I'm calculating the probability of a step up. The probability of an arrival is, or the likelihood, whether it's an arrival or not, that is, who wins the race, is independent of how long it took if the runners are exponential. And so that probability is the ratio of the arrival rate to the sum of the two rates. And then what must happen is, when I'm in my new state now, which is an exponentially distributed lifetime with parameter alpha sub j minus 1, that new state must last longer than h, or else I would have more than one transition. Okay, the rest of it is now arithmetic, because now I'm going to evaluate this integral. And so you can see nice things are going to happen. The alpha j's are going to cancel out. And what I'm going to have left is lambda sub j. So I took that guy outside the integral sign. And then I have e to the minus alpha sub j plus 1 times h. That's that guy right there. And then inside the integral, so I have the integral from 0 to h. And inside I have e to the plus alpha sub j plus 1 u times e to the minus alpha sub j u du. Okay? The h part has factored out. There's e to the minus alpha sub j plus 1 times minus u. That gives me e to the plus alpha sub j plus 1 times u. There's that guy there. The lambdas come outside, and the alphas have canceled. Yeah, I think that this board is too greasy, because I don't think it's these guys this time. Okay, lots of technical problems here. Okay, next step. Here's my alpha sub j, my lambda sub j. Here's my e to the minus alpha sub j plus 1 h. Now what I'm going to do is I'm going to fix this up by multiplying and dividing, so that I get in the denominator here, I'm going to get alpha sub j minus alpha sub j minus 1. Then I have the integral from 0 to h, and inside I'm going to put that alpha sub j minus alpha sub j plus 1. So this term and this term cancel, and then I'll combine those two exponentials, and that's going to give me e to the minus alpha sub j minus alpha sub j plus 1 times u du. Okay, so all I did was fix up this integral here by multiplying and dividing by that factor. The reason for that is that now when I look at this integral, I see that this is the integral of a density function of an exponential distribution whose parameter is alpha j minus alpha j plus 1. So that makes it easy to evaluate the integral. So continuing, what I have left here is lambda sub j divided by alpha sub j minus alpha sub j plus 1. That's this guy right here. E to the minus alpha sub j plus 1 times h. And then I evaluate this integral. Okay, now this integral, remember, is the integral of an exponential variable whose parameter is alpha sub j minus alpha sub j plus 1. And it integrates that between 0 and h, which means that it can be interpreted as the probability that an exponentially distributed random variable whose parameter is this lasts less than h. So that probability, therefore, would be 1 minus e to the minus alpha j minus alpha j plus 1h. Alpha j minus alpha j plus 1h. Okay, so This term in parentheses is simply this integral, which I evaluated without having to actually do any arithmetic by recognizing that this is the integral of a density function that's exponential between 0 and h. Okay, now I'll just multiply things out here. Okay, so what's left? I have lambda sub j, alpha sub j minus alpha sub j plus 1. Multiplying this out gives me e to the minus alpha sub j plus 1h minus, okay, now here I have an e to the minus alpha sub j plus 1h. Let me see if I drop the term here. No, I think I'm okay. So because of this minus sign here, that makes this positive. That's going to cancel with that. And so what's left is e to the minus alpha sub j h. So all I did was multiply this throughout, and I get this. Okay, one more step here. Lambda sub j divided by alpha sub j minus alpha sub j plus 1. That's this term. And now what I'm going to do is I'm going to expand this. So when I expand this, I'm going to get 1 minus alpha sub j plus 1h, and then plus all terms that are of order h squared or higher. And similarly, I'm going to expand this. And so the result is going to be that when I expand that and collect the terms, what I'm going to have left is alpha sub j minus alpha sub j plus 1 times h plus, because the 1's canceled, plus all the terms that are of h squared or higher. So those things are all O of h. Okay, so this thing in brackets comes from here by simply expanding this in the power series, expanding this in the power series, and then combining terms. So the term that's linear is going to look like this, because there's a minus sign here, and all the other terms are going to have h squared in them, so they're all O of h. Then I cancel out that with that, and what I'm left with is lambda sub j times h plus O of h. But that's what I wanted to prove. So in other words, what I just showed is that if all of the underlying variables that are racing against each other are exponentially distributed, then the probability that in a little interval of length h, the population size will jump by 1 is given by lambda sub j h plus little o of h, where h is the length of the interval and lambda sub j is the parameter that describes the exponential distributions for the lifetimes of the arrival processes. Well, that's the requirement for the birth and death process. By the same argument, we could calculate the other pieces, and that means that as long as all of the underlying variables are exponential, we have a birth and death process, and so now we can carry over all the machinery that we developed. So now we know that if everything is exponential, if all the underlying variables are exponential, then we can write rate up equals rate down, and we have the solution to rate up equals rate down, so now we can start using those probabilities. Okay, so this is just a straightforward probability argument. Any questions about this? Is there anything I need to clarify or repeat? Okay, so now we're ready, or we're getting to be ready, to actually get to the main stuff here. So let me erase this. Okay, so now we make the assumption that we have exponential variables, and so we know what the state probabilities are that define the resulting population. Okay, so now I'm going to define something, because we know what these probabilities are. Okay, so we have these PJs. PJ. Okay. So now I'm going to define what's called the carried load. And the carried load typically is called A prime. And by definition, it's the average number of busy servers. So average number of busy servers, that means that it's given by this formula. J Pj, well, I'll write it out in detail here. What it'll be given by is 0 P0 plus 1 P1 and so forth up to S minus 1 PS minus 1 plus S PS plus S PS plus 1 and so forth. Okay, average number of busy servers. So when the number of customers present in the system is less than S, then the number of customers present is equal to the number of busy servers. But when the number of customers in the system is S or more, then the number of busy servers is S, because the additional customers would be waiting in the queue. So this thing, the sum of JPJ plus the sum of SPJ, where the first sum is for J less than S, and the second sum is for J greater than or equal to S, that's the average number of busy servers. Now, obviously the average number of busy servers can't be greater than the number of servers there are. If all the servers were busy all the time, then the carried load would be equal to the number of servers. So that's the maximum value that the carried load can be. So we measure the carried load in units that are called Erlangs, after A.K. Erlang, the father of queuing theory. Okay, so these are called Erlangs. So if I say I have a group of servers and the average number of busy servers is 8, let's say, that means that I'm carrying 8 Erlangs. Then I can define the utilization, or the occupancy. So the utilization is called rho, and by definition, it's the carried load divided by the number of servers. So if I have a system with 10 servers and it's carrying 8 Erlangs, that means the utilization is 80%. So one server busy all the time is carrying 1 Erlang of traffic. One server busy half the time is carrying half an Erlang of traffic. So the Erlangs are the measure of how much traffic is carried. Now also, we have a measure of how much traffic is offered. We call that the offered load. And there's a formula, it's called A, and the offered load is given by the arrival rate times the average service time. And that also is measured in Erlangs, and it'll turn out that offered and carried load are related in the sense that, there's a certain load that's offered, and if the capacity of the system were such that all the customers who arrive ultimately get carried, then the offered load and the carried load are the same. And if some of the customers get lost, then the offered load is bigger than the carried load. So we'll see how that works out in particular cases. But right now I'm just giving these concepts and formulas. There's the carried load measured in Erlangs, which is a measure of how much traffic or how much work the system does. There's a utilization, which is a measure of how efficient it is. And then there's the offered load, which is a measure of how much traffic is offered to the system. And we'll see, although it's not clear from this, that there's a relationship between carried load and offered load. And that's going to relate to the probability of loss. There's a question? Could you repeat that?
Can you please state it again? What is the relationship between carried load and offered load?
Okay, at the moment, the question is what's the relationship between carried load and offered load? At the moment, there is no apparent relation because the carried load is the average number of busy servers. So it's some measure of how much work the servers are doing. The offered load is the product of the arrival rate and the average service time. Obviously, it's a measure of demand because as we saw before, like in homework 1, as the offered load gets bigger, that represents more demand, more requests for the use of the system. It'll turn out that the carried load or the offered load is in fact the load that would be carried if there were no losses. But we have to show that. So We can show that in special cases, and also that's an example of what's called Little's theorem, which is very important, which we'll get to shortly. So right now, the names offered and carried load indicates that there must be some connection, but the formulas don't show what those connections are. So what we have to do now is we have to look at systems like the Erlang loss system and the Erlang delay system and other systems and take the specific probabilities, put them in these formulas, and then from that calculate the carried load, the utilization, the offered load, the probability of loss, and all the other stuff. Okay, that's the big picture. All right, now there's one other thing we have to worry about, one of the theoretical aspects before we can get to that, and that has to do with what the interpretation of these probabilities are. Because remember, we talked about the viewpoint of the arriving customer and the viewpoint of the outside observer, and they're not necessarily the same thing. In fact, we showed that in homework 1, because in homework 1, what we calculated by simulation was we calculated the fraction of customers who, when they arrive, find the blocking state. We calculated the fraction of time you were in the blocking state. And we saw that if the arrivals were generated according to a Poisson process, those two things turn out to be the same. That's a theorem which I now want to investigate a little bit better. That's called PASTA. And it turns out if they're different, then in general, those two measures, those two probabilities are different. Now, what the birth and death probabilities give you are the so-called time probabilities. The PJ here is the fraction of time that the birth and death system is in state J, if you're looking at a system in equilibrium over a long period of time. But we don't really care directly what the fraction of time the system is in each state. What we care about is the fraction of customers who arrive when the system is in that state. But those two things, in fact, if you think about it, should be different, because when a customer arrives, he makes the system change its state. So customers arrive just at the instance before the changes of state occur. And so therefore, they're obviously not arbitrary instants, they're very special instants. So in fact, it seems very surprising, if you think about it, that if the arrivals occur according to a Poisson process, the two probabilities turn out to be the same. So when I first learned this, my view at first was that to say that the viewpoint of the arriving customer and the outside observer is the same is obvious, because the difference is just semantics. But then when I understood exactly how you compute this, I said, that's amazing, it should never happen. And then it turns out that, well, yeah, it happens sometimes. It happens when the input process is Poisson. Actually, it happens more often than that, but the other cases are sort of bizarre. Okay, so let me look at this issue. And this now is in section 3.3.2. What is it in our book? 3.2. All right, so here we are. So now we're coming to a very important theorem. Okay, so in our textbook, it's section 3.2, and it's called the relationship between the outside observer's distribution and the arriving customer's distribution. So this starts on page 77. Now in the textbook for the course, the other textbook, which is the Bertsekis and Gallagher book, B and G I'll call it, this is actually section 3.3.2, and this is on page 171 to 173. Yeah. What's that? Camera just went off. Camera just went off. Technical difficulties. We're taking a break here while they... I don't know what's going on.
I think the lamp bulb blew out, so that one's still on. I'll be an engineer to come with that real quick.
So should I wait for you?
No, they're still recording and they have one screen. Just have to get this one trying to work.
Oh, okay.
Everything's still being recorded.
Same thing for the DVD. Okay. All right. So while we're worrying about that, can you read what's on the board? Because it seems to me that somehow or other this isn't as dark as usual. They must have washed the board with something that's... you can read it? Okay. All right, so remember at the beginning of the course what I said we were going to use this book by Bertzekis and Gallagher, the one called Data Networks, and that I would try and link the two books together. So what we've been doing so far is background material, which Bertzekis and Gallagher sort of assume. And they don't really develop things the same way because they're not really concerned so much with the development. They want to get right down to the answers. So they do this in their chapter 3. And what I'm talking about now is section 3.3.2 in their book. And so it covers the same subject. Now, the thing that I'm talking about is what's called PASTA. All right, so this is a statement. If Poisson arrivals then pi j of t, which I have to define, is equal to pj of t. Now, pj of t, by definition, that guy right there, that's the probability that the number in the system at time t is equal to j. Actually, we're generally interested in this in the limit as t goes to infinity, but it's true for any value of t. So these are the probabilities that come out of the birth and death equations. By definition, this is the conditional probability that given that the system, that t is an arrival point, that the system is in state j. So this is the unconditional probability that at time t the system is in state j. This is the conditional probability that given that t is an arrival point, that the system is in state j. So let me write down that definition more formally. And the equality, by the way, the fact that this is true, this is what's called PASTA. Now, Bertzekis and Gallagher don't mention that word. I'm not sure why not. The reason that it's not mentioned in my book is because it wasn't coined at the time that book was written. So this PASTA theorem was first proved to the acceptance of most people as being a rigorous proof. The PASTA theorem was first proved by Wolff, W-O-L-F-F, in 1982. And that reference is given in the Bertzekis and Gallagher book, but they don't use this word. And what it stands for is Poisson arrivals C time averages. So the time averages, that's what the birth and death probabilities represent. And what this says is that if the arrivals occur according to a Poisson process, then when they arrive, that distribution is in fact what they see, even though they arrive at the points that are exactly those points at which the system makes its transitions up. Okay, now I want to prove this, at least in an intuitive way. This theorem was actually known for many years, but Wolff, I think, kind of nailed it down to the satisfaction of mathematicians. So let me define pi j of t. Or this is sort of an intuitive definition. This is going to be my proof. So this proof existed well before Wolff's, but it's not rigorous. I think I'll try and convince you why that's true. So here's what this is. Suppose that I have an interval. So this is t, and this is t plus h. And at time t, the system is in state j. And I'm going to assume that a customer arrives between t and t plus h. And then I'm going to let the h go to 0 so that this customer's arrival point is pushed so it's just infinitesimally to the right of the point t. And then I want to calculate the conditional probability that given that this customer arrived in this interval of length h and then the h goes to 0, the probability that the point t, which is just prior to his arrival point, the probability the system is in state j at that time is given by the unconditional probability of being in state j at that time if this arrival occurred according to a Poisson process. So here's the definition. It's the limit as h goes to 0 of the probability that the number in the system at time t is equal to j, given the condition that between t and t plus h, I have an arrival. Now, the notation that I'm using here is not probably the best, but it's what was used in the book. Wolf calls this A, which probably makes more sense. I meant customer arrives between t and t plus h. If you use an A, that sort of says arrival between t and t plus h. So this says, given that I know that an arrival occurred between t and t plus h, find the conditional probability that at time t, the system was in state j. And if I let h go to 0, that means I'm forcing this arrival to occur just after the instant time t. So therefore, that's what this guy finds. Okay, so this is going to be our definition of the arriving customer's distribution. So this guy right here, let's see, the pi is the arriving customer. It's what he sees. And the p, this guy and this guy, they're the same thing. That's the outside observer. Okay, but the first thing I want to do is I want to look at this for the case of Poisson input, and then I'm going to look at it in general. Because it's going to turn out that we're going to need to know, have a formula for the arriving customer's distribution for cases in which we do not have Poisson input, but we still have a birth and death process. That'll turn out to be one of the important models. Okay, so suppose we have Poisson input. If we have Poisson input, then we can write the following. What's the probability that in the interval of length h between t and t plus h, what's the probability that in that interval a customer arrives, given that at the beginning of the interval the number in the system was j? And the answer is, well, if we have Poisson input, we know that the probability that we have an arrival in any little interval is independent of everything except the parameter that describes the arrival process and the length of the interval. But it does not depend on time, does not depend on the system state, doesn't depend on anything. In fact, it's lambda h plus little o of h. So the point is that the probability that I have an arrival between t and t plus h, given that at the beginning of the interval I was in a certain state, if we have Poisson input, that's the same as the probability that I have an arrival between t and t plus h. Because whether an arrival occurs in any little interval does not depend in any way, by assumption of a Poisson process, does not depend on the state of the system at the beginning of the interval or any other time. Okay, so what does that mean? That means that the event, a customer arrives between t and t plus h, and the event, the system is in state j at time t, these are independent. Because what do you mean by independent? Two events are said to be independent if the conditional probability of one of them, given the condition, is the same as if you're not given the condition. That's what you mean by independence. That's what motivates the definition of conditional and the concept of conditional probability and independence. So, if A is independent of B, then B is independent of A, as you learn when you learn conditional probability in an undergraduate course. So that means that if I reverse these things, that should also be true. So if they're independent, then therefore the probability that the number in the system at time t is equal to j, given that a customer arrives between t and t plus h, that must be the same as the probability that the number in the system at time t is equal to j. Now, the definition of the arriving customer's distribution was exactly this in the limit as h goes to 0. Of course, the limit doesn't matter here because we just showed that the h is irrelevant. So what that means is that this thing right here, that's pj of t by definition. This thing is pi j of t. So pi j equals pj if we have Poisson input. Okay, so that's the rock and roll version of the Pasta theorem, which says that pi j and pj are equal if we have Poisson arrivals. Okay, now why is this, what's wrong with this? Why is this not a really rigorous, legitimate proof? And the answer is, well, go back over here and look at the definition. This is a conditional probability, and we're conditioning on an event which in the limit as h goes to 0 has probability 0. And you know that when you study conditional probability that you're always told something like this in the elementary textbooks. The probability of E given F is the ratio of the probability of the intersection of E and F to the probability of F, and then they always state if the probability of F is greater than 0. Of course, undergraduates ignore that, but what it says is that if this is, the denominator is 0, then you have, well, then it's undefined. So you have to worry about whether the numerator is also 0 and how, and of course you can't just plug in 0 over 0. You have to be very careful about it. Now, if the random variables we're discussing are continuous, then the probability that the random variable takes any specific value is 0. So in the limit as h goes to 0, that's then the probability that this event occurs at a specific point. And the probability that the arrival occurs at any specific point is 0. So therefore, it's problematic to be able to, or even to use this definition, or even understand what it means. Because if you think about it, when you're talking about a stochastic process, there's a different stochastic process for every value of t. There's a different random variable that describes the state of the system at t. And the theoretical foundation of stochastic processes is to show that a stochastic process exists. Because in a stochastic process, what you have is an uncountably infinite number of linked stochastic processes, because there's one for every t, and t is uncountable. So this gives you the stochastic process problem. This is the mathematics problem. But the common sense view is, well, of course, what's going to happen here is that as h goes to 0, the denominator is going to go to 0, but so is the numerator going to go to 0. Something's going to go to 0, and so the ratio should be okay. And so, in fact, that's what's going to happen. But Wolf was the first one, as far as I know, to discuss this in a way that makes mathematicians happy, although everybody knew it was true for many years before that. Maybe that's sort of ordinary, the way mathematics develops. Okay, so now what I want to do is, now that I've proved that at least for Poisson input I'm okay, now what I want to do is look at this thing right over here in general. So what I'm going to do is I'm going to take this conditional probability, I'm going to rewrite it using Bayes' rule, then take the limits, and then get a result, which we're going to use later on. Okay, notice that so far, the only assumption I've made is that it doesn't even have to be a birth and death process for what I've done here. The only assumption I've made is that the arrival process is a Poisson process, meaning that the probability of an arrival in any interval of length h depends only on the parameter of the Poisson process and does not depend on the absolute value of the time or the state of the system. As long as we have that, then we have pasta. Okay, so now let me rewrite this so it's all on one board. The probability that a customer who arrives at time t finds a system in state j is given by the limit as h goes to 0 of the following conditional probability. The probability that the number in the system at time t is equal to j, given that just after time t, the customer arrives. In other words, given that t is not an arbitrary point, but is an arrival point. Okay, now that's a conditional probability, so I'm going to rewrite that using Bayes' rule. So let me write it down, and then I'll discuss Bayes' rule if necessary. But again, this is the standard stuff that every undergraduate course has. Okay, so in Bayes' rule, what you do is you first write the conditional probability from its definition, which is the ratio of the probability of these events jointly, that would be in the numerator, divided by the probability of the event on which I'm conditioning. And then you use the theorem of total probability and the definition of conditional probability again to get this in a specific form. Okay, so the denominator, let me write the numerator first. The numerator, this would be the probability that, put some brackets here, the probability that a customer arrives between t and t plus h, given that the number in the system at time t is equal to j, times the probability, consistent here, times the probability that the number in the system at time t is equal to j. That's the piece of probability that n of t equals j. So if I were to rewrite this as a ratio and then cancel out the denominator with that, what I would get would be the joint probability of this. Okay, so using Bayes' rule, the idea, remember, is that what you do is you switch the event and its condition and put that in this ratio. What about the denominator? The denominator is exactly the same stuff, except that you're going to sum it over all possible values of j, or in this case, let's call it k. So this is going to be the sum of the probability that a customer arrives between t and t plus h, given that the number in the system at time t is equal to k, times the probability that the number in the system at time t is equal to k, summed over all k. So this statement right here, this is just the Bayes' rule, or Bayes' theorem, or Bayes' formula rewrite of that conditional probability. In the textbook, this is equation 2.3. Okay? Okay, so this looks like a lot of stuff I wrote down. Is there any question about Bayes' rule? You want me to say something about that? Here's Bayes' rule. Suppose we have a sample space and we have a partition. Say F1, F2, F3, F4, and so on. Could be any number of these guys. And a partition means that it's like a jigsaw puzzle. So that the F's cover the whole space, and there's no overlap, which means that when the experiment is performed, you get a point in the sample space, so exactly one of the F's must occur. And then there's some event E inside there. And I want to calculate the probability of E. Well, let's see. First, let me calculate the probability of E. All right, let me calculate the probability of E. Okay, the probability of E, as you remember, and this is sort of kind of obvious now, can be written this way. It's the probability of F1 times the probability of E given F1 plus the probability of F2 times the probability of E given F2, and so on. And the interpretation of that is I could say, well, what's the frequency with which E occurs? Well, it's the frequency with which F1 occurs multiplied by the frequency with which E occurs if F1 occurs, plus the frequency with which F2 occurs multiplied by the frequency of E if F2 occurs, and so on. So this gives me the probability of E. So suppose I wanted to calculate the probability of, let's see, of F sub I, let's say, given E. That is, I know that E has occurred. I'll get a condition on that. And I know that one of the F's must have occurred. And I want to know the probability that the particular F that occurred is this one. So from the definition of conditional probability, I would write that as the probability of the intersection of F sub I and E divided by the probability of E. Now, in the denominator, I'll expand the probability of E as we did here. So it's the sum of the probability of F sub k times the probability of E given F sub k. That's the theorem of total probability. So that's that. What's the numerator? Well, the numerator can be written as the probability of F sub I times the probability of E given F sub I. Why is that? Well, because if I apply the definition of conditional probability here, I get the probability of the intersection of those two divided by the probability of F sub I. The probability of F sub I would then cancel out, and I would be left with the probability of the intersection, which is right here. So starting with the definition of conditional probability, this derives from Bayes' theorem. So this over here is simply the Bayes' theorem in which the partition is the state of the system, because at time t, I must be either state 0, state 1, state 2, and so forth. So what I'm calculating here is this is the conditional probability that I am in state j at time t given that an arrival occurs. And now here I've switched things because here I'm given the state and asked for the probability of the arrival. So I switched the two events, just like I did here, and this is then Bayes' rule. So this is straightforward. Okay, now let's assume that we have a birth and death process. Okay, so now I'm going to take these conditional probabilities and I'm going to replace them as follows. What's the probability that if the system is in state j at time t, that is in state j at the beginning of the interval, that an arrival occurs, a birth occurs. And that would be equal to, if it's a birth and death process, lambda j h plus little o of h. Here's my pj of t. What about the denominator? Well, the denominator looks the same way. It's the sum over k of lambda sub k h plus little o of h times p sub k of t. Okay, so as h goes to 0, these guys right here, these are the probabilities of having a birth in the interval of length h, because at the beginning of the interval I'm in state j, and I want to have the probability that if I'm in state j at the beginning of the interval, that a birth occurs, that an arrival occurs. Okay, so that gives me this, assuming that I have a birth and death process. Now what I'll do is I'll divide through by h, and then I'll let h go to 0. When h goes to 0, of course, that goes to 0, that goes to 0. And what I'm left with is lambda j pj of t divided by the sum of lambda k pk of t summed over all k. Okay, so what we have just proved now is the following. If I have a birth and death process, the probability that the system is in state j at time t, if t is an arrival point, is given by lambda j pj of t divided by the sum of lambda k pk of t, where the p's on the right-hand side of the equation are the solutions to the birth and death equations. In particular, if I let t go to infinity, which is the case I'm most interested in, I get pi j, the probability that an arriving customer in equilibrium finds a system in state j is equal to lambda j pj divided by the sum of lambda k pk. So I take the birth and death equations, I solve them, and the solutions are the p's. I put them in this equation, and whatever that turns out to be, those are the pi's. So that's the relationship between the equilibrium probabilities as seen from the viewpoint of the outside observer and the equilibrium probabilities as seen by the customers when they arrive. Okay, as a check, suppose we have Poisson input. Suppose the arrivals, the birth process, is a Poisson process. Suppose Poisson input. Then pi j is equal to, if it's a Poisson process, that means that the birth coefficients are independent of the state of the system. So lambda j is replaced by lambda. The denominator is the sum over k of lambda pk. In general, the birth coefficients can depend on the state of the system, but they don't have to. In fact, that's the important case in which they don't. That's the case in which the arrivals occur according to a Poisson process. Then the birth coefficients are constant, so we call them lambda. The lambdas cancel. The denominator then sums to 1. And so we get pj. So if we have Poisson input, the arriving customer's equilibrium distribution is equal to the outside observer's equilibrium distribution. So in homework 1, where we had the Erlang loss system, the fact that it was Erlang loss was not relevant here for this question. If it was an Erlang loss system, the point was that if we had Poisson input, then the states as seen by the arrivals have the same probability distribution as the states as seen by an outside observer. And in the simulation, the outside observer was represented by calculating the fraction of time. That is, we looked at the system over all time and calculated the fraction of time we were in a particular state, in that case the blocking state. And to calculate the arriving customers distribution, we calculated the fraction of arriving customers who found the blocking state, and they turned out to be the same thing if we had Poisson input. So this now proves that, or at least it proves it if you're willing to accept this definition, which is mathematically problematical because it conditions on an event whose probability is 0, a set of measure 0, as they say. Okay, any questions about that? All right, so now we're actually ready to start looking at at a real system, which is the Erlang loss system. That's the next one. So this is in the book, and let's see where I am. Okay, so we've just covered section 3.2. We're up to section 3.3, where we now start actually using this stuff. Okay, so now we're going to go to the Erlang loss system, which is the one that we've already analyzed in part. This was what you did in homework 1. But now, presumably, you have a better understanding of what it is you were doing. Okay, at least that's the intent. Now, if I were teaching this course, let's say to undergraduates, or from a more applied point of view, we could have taken the last couple of lectures and skipped them and just said, okay, rate up equals rate down, let's believe it, and now let's derive the formulas from it and compare them with simulation, and it all works. But that's a cheap way out of it. Okay, so I'm in section, what did I say, 3.3. So I assume there are no questions. I always say that just as I erase things. So this is called the Erlang loss system. All right, so we have a birth and death process. We have Poisson input. We'll assume exponential service times. So that means that now we know that we can write rate up equals rate down. Now, if we have Poisson input, that's the assumption we make for an Erlang loss system. If we have Poisson input, that means that the lambdas are constant. If we have exponential service times, okay, that means that now we have to find the death coefficient. The death coefficient, remember now, corresponds to the parameter of the minimum of the exponential variables that represent the service times. Because when the service times expire, that's when the deaths occur. A service completion is a death. So we assume that if we're in state J, that means that there are J customers in service simultaneously. So if each of them has parameter exponentially distributed service time with parameter or average value tau, then the parameter is mu 1 over tau. So in this case, we'll define mu sub j as equal to j times 1 over tau, or in other words, what we'll call j mu, where mu is the reciprocal of the average service time. Because the birth coefficient corresponds to the parameter of the minimum of the j, because we're in state j, exponential service times. This is wrong, by the way. I should have said j plus 1 right here. Rate up from state j, rate down from state j plus 1. Okay, so now we write these equations. They are lambda pj is equal to j plus 1 over tau pj plus 1, for j equals 0, 1, and so forth up to s minus 1. Those are all the equations. We already did this, and we find out that pj, the equilibrium probability, is equal to, well, if I'm going to let a equal lambda times tau, then when I solve these equations, what I get, as you already know, is a to the j over j factorial p0. And p0, what makes everything sum to 1, is the sum of a to the k over k factorial as k runs from 0 to s. So these are the state probabilities for the Erlang loss system, assuming we have exponential service times. Now we have a theorem that says, this is the amazing theorem which we haven't proved but we'll get to later, that says that this result holds even if we don't have exponential service times, and you already proved that or saw evidence for that in homework 1 when you simulated it with exponential service times and constant service times, and you saw that as long as you had Poisson input, you got the same answer. So this represents the state probabilities, and by pasta, the pi's, which represent what the customers see, is the same thing. Now, you already know all this. Now, one of the things that we wanted to define in order to be able to understand the behavior of such systems is the carried load. The carried load was the average number of busy servers. So it's given by the sum of j pj for j less than s plus SPJ for j greater than or equal to S. So in order to calculate the carried load, I now have to plug into this formula these probabilities. Okay, so I do that. The sum, and now, well, I'll just write it out like this. It's going to be equal to 0 P0 plus 1 P1 up through SPS. Because the way this sum is written, this last term is the first term in the sum. And now I take these probabilities and I put them in here and I do some work. And when I get done, the answer turns out to be A times 1 minus B of S and A. This is just algebra to do that. And in fact, this is given in the book. This is equation 3.5 in the textbook. And there's an exercise here, which, let's see, I forget where it is, but it says, let's see, exercise 3. Yeah, exercise 3 says show that this is true. Okay, so you plug the probabilities that we got from rate up equals rate down into this equation, you get that. You can look that up in the solutions manual. That's the same thing as A minus A B of S and A. All right, so this is kind of interesting. This says that the carried load is equal to the thing called the offered load multiplied by the fraction of the load, offered load, that is in fact carried. Because this is the probability of loss. Remember, it's the probability of blocking, of being in state S, but because of pasta, it's also the fraction of arrivals that find state S, and therefore it's the fraction of arrivals that are denied service or are lost from the system. So 1 minus that is the fraction that's carried. So the carried load is equal to the thing that we called the offered load times the fraction of the offered load that is carried. But that helps us understand why we want to call this offered load. Because suppose I had an infinite number of servers. If I had an infinite number of servers, then this probability would be 0. The fraction of customers lost if I have infinite capacity is 0. So that means that if I have infinite capacity so that everybody who arrives gets served, the carried load is equal to the offered load. So the offered load is the load that would be carried completely if the number of servers was large enough so that everybody who arrived gets served. It makes perfect sense. So that means that the carried load can be viewed as the offered load minus the lost load. Okay, this is carried, offered, lost. So the number of Erlangs carried is the number of Erlangs that's offered minus the number of Erlangs that's lost. I can solve this equation for B of S and A to calculate the loss probability. And it turns out, as you can see, by just simple arithmetic, that the fraction of customers lost is the offered load minus the carried load divided by the offered load. That comes right out of here. So that makes sense. Or it makes sense, it could make sense. Intuitively, it's what you would like because it's simple. Of course, it could be wrong, but it works now because of pasta. What it says is the fraction of calls or arrivals that are lost is the amount, is the difference between what is offered and what's carried. That's the number of Erlangs that's lost divided by the number of Erlangs that's offered. Okay? See, did I do that right? This is what's offered. This is what's carried. So the difference, no, wait a minute. Let's see. I want the lost load. Maybe instead of memorizing things, I should derive things here. Okay, so I'll bring this over to the left-hand side, and then I'll have A minus A prime. No, that's right. And then I will divide it by A. That's equal to 1 minus A prime over A. Okay, so A prime is the carried load. A is the offered load. The ratio is the fraction that's carried. 1 minus that is the fraction that's lost. That's the Erlang B value. Okay, so part of the point here is that this makes perfect sense. Okay, so now intuition comes into play. Now you can see what's going on. Okay, now let's look at some of the exercises. In particular, I want to look at exercise 6 on page 82. Exercise 6, page 82. Exercise 6, page 82. And the question is, I want to be able to calculate the Erlang B. We already have a formula for it, but suppose that S is large. Suppose S is 100. Suppose I have, let's say, suppose I ask this question. How many servers do I have to provide if I have 100 Erlangs of offered traffic such that the fraction of customers or calls that are lost is no more than 1%? That's the kind of thing that the teletraffic engineer wants to know. You have an estimate of the demand in Erlangs. You have a probability of blocking a criterion, and you want to know how many servers to provide. So suppose I said you have 100 Erlangs of traffic. If you have 100 Erlangs of traffic, that means that if there were no blocking, you would be carrying 100 Erlangs. But you're not going to carry 100 Erlangs here because you're going to have 1% blocking. You're only going to carry 99 Erlangs. So if you're going to carry 99 Erlangs, how many servers do you need? Well, obviously you're going to need at least 100 servers. So in order to make this calculation, I'm going to have to, it's going to be very complicated, and I'm going to have things in here with factorials and powers of the order of 100. Suppose I want to add 1,000 servers. I mean, modern times you can have 1,000 servers, 10,000 servers, so how are you going to do that? So the answer is, well, there's a nice simple recursion which allows you to do it, and one of the exercise asks you to prove that the following is true. That this formula is given by the following. A B of S minus 1A divided by A, let's see, divided by S plus AB of S minus 1A. So this is a recursion because now I'm going to calculate this for S equals 1, 2, and so forth with the initial condition that the Erlang B for A Erlangs and 0 servers is equal to 1. So it's very easy to write a program that says, okay, set B0 equal to 1, calculate B1. Then put that in here, calculate B2, calculate B3. You can calculate the Erlang B for thousands of these things in an instant with complete accuracy. The way to prove this is you take the formula for Erlang B, you put it on the right side, you cancel things out, and you show that it turns out to be the same as what's on the left side. So from now on, if I ask you to calculate the Erlang B, I don't want you to use the curves. That's just an estimate. I don't want you to plug into a formula with gigantic powers. I want you to use something like this. In fact, here's an example. I'll do this in class next time. Okay. Find the minimum value of S such that the Erlang B for that value of S and 100 Erlangs is no more than 1%. Anybody want to give me an estimate? How many servers do I have to have so that if I have 100 Erlangs of traffic, no more than 1% of it is lost? Is that going to be like 200 servers, 110 servers, 500 servers? Okay, it's easy to write a program to calculate this because all I have to do is calculate the Erlang B for 100 Erlangs until for the first time, for each value of s, until for the first time I find a value of s such that the left-hand side is less than 1%. And then I quit. That takes like an instant. If you had to do this by hand or by using the formula directly, you'd never get done. Okay, so I'm going to start with this kind of stuff next time. So where we are is we got all the theory out of the way, and now we can look at the Erlang B model, the Erlang C model, and some other models as well, and get a much better understanding of what these probabilities mean. And for homework 3, which you could start looking at, I'm going to be looking at the Erlang C model, which is the one in which we allow queuing to occur, and we'll look at the formulas. We'll derive them in class, and then I'll ask you to compare it with simulation, just like in homework 1, except that in homework 3, I'm going to put the burden on you to change the simulation so that the queuing is accounted for, although I'll show you a trick, which I think is an easy way to do it. Okay.